Everyone. There we go. Hi, everyone. So I'm Chelsea. I'm here today to talk to you about some of the work that I did during my PhD dissertation, which concluded last year. So this title is pretty long. We're going to talk about more so characterizing and linking two phases of wildland fire lifetimes from Siluca district in Ontario. Today we're going to talk about mainly the multi-state modeling techniques, but I will mention the joint frailty modeling that we are doing as well. So just to kind of motivate this work, it was done with my two supervisors, Charmaine Dean and Doug Wolford, along with Colin McFadden, who's from the ministry, and I'll talk about the ministry more in a few moments. So just to motivate it, and you can't see maybe the top because of the Zoom slide, but wildland fires, right? Pretty newsworthy always, but especially this summer, we've heard about wildland fires even more in the news with all of the fires that were happening and the smoke plumes that were coming across Canada, the US, and even into Europe, right? So quite a lot of attention being drawn this fire season. So a fire lifetime itself goes through kind of different milestones. And of course, we have the ignition of the fire all the way until it is put out. And so what we decided to do was split up the fire lifetime into these kind of key phases. And so in collaboration with members of the Ministry of Northern Development, Mines, Natural Resources, and Forestry, we came up with these two phases. So the first is the detection phase, which runs from the ignition to the report. And the second one is what we call the action phase, which is from that report until it gets into a status of under control. And we left out. And the reason being is something that we can talk about later if it's of interest to you. So the main questions that we wanted to answer or investigate was how different factors affect the time spent in these various phases, and how the distributions of time spent in them are connected to one another. So essentially how the phases are connected. So let's talk about these wildland fires in particular. So as I said, this is data coming from Sioux Lookout. It's a district in the Northwest Fire region. And so you can see on the inset, it's pretty, Northwest in Ontario. These are all the data that we have plotted within the region. And if you're curious as to the icons, the yellow squares, triangles, and diamonds at the bottom there, those are the fire management headquarter attack bases and forward attack bases. So essentially stations that the ministry uses to send out resources from. And you can see they're mainly located in the southern part of this district. So fire management agencies like the ministry, I'm going to refer to the ministry as the ministry because they have a quite long title. They have to decide how they manage the wildland fires across Ontario. And so in past, they had a system of response that included full suppression, partial suppression, and monitoring. In the past few years, they've actually moved away from this type of structured response, and instead they've moved towards what's called appropriate response. And again, we can talk about that if it's of interest to you. So the work that we did, we focused on full suppression fires. And the reason being is because these fires actually progress through all of those milestones. So they have that complete phase that we were looking for. Ones that are monitored kind of have a different progression of their lifetime. So here we're focusing on those fully suppressed fires. And our data contained about over 2,000 fires that were fully suppressed from '89 to 2019. And so wildland fires, it's well known that there's kind of two typical causes of them, one being human causes and the other being lightning. And you can look at the distributions of those two phases for the human and lightning caused fully suppressed fires within Sioux Lookout. And it's well kind of suggested that you study lightning and human caused fires separately due to kind of their inherent differences of those fires in terms of location, detection as well, right? You can think of like fires that are lightning caused. Sometimes they happen in really remote places. And so they're not recognized or detected until much later on. So we decided to separate them. Now, the data that we have, it's quite rich. And so we decided to kind of categorize the different variables that we had available to us into these 5 different categories. So we have fuel moisture, which is coming from the Forest Fire Weather Index system variables, and I'll mention and talk about those in a moment. We also have the type of fuel that the fire is burning, So that's grass, coniferous, mixedwood, or other. We have some temporal aspects, such as when the fire was ignited, which season, the time of day it ignited, and so on. We have some distance aspects, such as where it's located in comparison to those fire management headquarters or other locations within the district, along with nearby roads, and some other information as well. So fire load being the number of fires that are currently burning on the landscape at the same time as a specific fire. So along with the size of the fire at initial attack, the number of ground forces that were needed to fight that fire, and so on. So as I said, this is the fire weather index system, and you can see it's essentially taking an input that's weather observations, and then it produces these 6 codes or indices, and they give us a sense of how fire will behave based on the different scales of these codes. And in fact, fire managers have these codes available to them every day, and they are used within their decision support tools as they assess how they're going to handle that fire moving forward. So the first way that we decided to kind of model these lifetimes was to use multi-state modeling. And of course, with multi-state modeling, the 2 features of interest that we had were the continuous time transition intensity functions, which are they represent the instantaneous rate of progression from, to state, in this case, L, conditionally on occupying state K, of course, given that history as well of all the events that it has been in, along with the transition probabilities here. So for an individual eye, or for us, it's a fire eye, the model that we used was one where the predictors act multiplicatively on the intensity. And so we split it up in this way. We would have our baseline and then our function G, which is a function of the fixed predictors along with the coefficients. And with this, we decided to use a common choice for that function. So we used the exponential, and this way our multi-state model followed a similar framework as our Cox proportion hazards model in survival analysis. And as well, we can note that it would be Markovian, of course, if it depends on the state that it's in currently, right? So with our multi-state model and the way that it's set up, it was pretty nice and straightforward. We had a 3 progressive process multi-state model. So the 3 states that we have are the ignition time, report time, and under control time. The detection and action phases are essentially moving between those 3, between those 3 states. We have our unspecified baseline transition intensity function, and our time T is, as I said, that detection or action phase, depending on which transition we're talking about. So if we pull out a specific Pth predictor here, we can look at what happens when we have a positive coefficient versus a negative coefficient, just to see how we actually interpret the results of the multi-state model that we have. So when we have a positive coefficient here, the hazard function, the hazard ratio, which is the exponential of that coefficient, is greater than 1. And so as the Pth predictor increases, the hazard function increases, and that results in a faster decrease of our survival function. And when we put that into the context of our wildland fire lifetimes, that results in a shorter, or it's associated with a shorter fire lifetime phase, with all of the other predictors being held constant. And we have the opposite association happening when we have these negative coefficients. So here we're focusing, these are the results for the human-caused fire, so the human-caused 3 progressive multi-state model. And so you can see I've split up the results here between the 2 phases. We have the information for the 5 different categories. We only used 4 for detection in the end. And then we have whether it's that variable is associated with a shorter phase or a longer phase. And so here we're just kind of categorizing things, right? Categorizing what variables are influencing these 2 phases. And so if we take a look, I'm not going to read through all of them, but some that are interesting that I like to point out would be the ISI, or the initial spread index. So the initial spread index we can see is associated with a shorter detection phase and also with a longer action phase. And so what that means, right? Initial spread index, essentially as that variable is increasing, the fire is spreading more, has more ability to spread. And so if we think about a fire that's spreading more in terms of detection, it kind of makes sense that it's associated with a shorter detection phase, because you can imagine a fire that's spreading more, it's emitting more smoke and it's making it easier to have that detection. Whereas if we think about spread in terms of action, a fire that's spreading more is a lot more difficult to action on, right? If we think about the temporal aspects, in particular the seasons, so here we see that fires that were ignited in spring have shorter detection phases than those ignited in summer, and fires ignited in the fall have longer detection and action phases than those ignited in the summer. So again, if we kind of see what's happening here, spring we know has a lot of green up effects, right? So the trees have that new beautiful growth, and so that adds more fuel to, adds more fire to the flame, we could say. And so, yeah, we're getting, again, more fuel, more smoke, and that shorter detection. Whereas when we see fall coming in fall, in terms of detection, that's often when aerial crews that were on contract are let off. And so you have less people going out to do that detection. As well, the days are getting shorter, so we have less sunlight, and those crews only go out during hours of sunlight, right? So the detection times themselves have shortened, which can result in those longer detection phases. And as well, for actioning, the crews that have are going out to fight those fires are typically somewhat let go in the fall. They do keep them on hand, but there's less resources, right? So we have these longer actioning phases compared to during the heat of the summer. Now, the interesting one here is that we actually used the detection phase as a predictor for the action phase. And so we see that as the detection phase gets longer, it's associated with a longer action phase as well, right? So we're seeing this kind of interesting relationship between the two phases. And of course, we can look at the estimated transition probabilities across the different states. And this isn't always my favorite part because it's kind of telling you what the multi-state modeling is doing. It's pretty obvious, right? We can't stay where we are. It has to progress forward. And with the multi-state models that we're doing, right, they can't go back. We can't have a fire that, you know, was reported and then goes back to ignition, right? That doesn't happen in this case. So they're not the most interesting plots for us to focus on, but nice to kind of remind ourselves of the process that's happening. More interesting perhaps is the time scale at the bottom, right? We can see, especially for human fires, that these are happening pretty quickly, within 2 days or less, right, for the estimated transitions. So then we turn to joint frailty modeling to model the relationship, to model the phases of these lifetimes for our wildland fires. And so the hazard function that we used is kind of similar to what we saw with the multi-state modeling, right? We're trying to keep that Cox proportional hazards framework between both techniques that we're using, where here our time TAJ is the fire lifetime phase duration, where it's going to be the detection phase when J is equal to 1, and it'll be the action phase when J is equal to 2. But the critical addition that we have with this joint frailty modeling is that we have these fire specific frailties that are included, where we can have this fire to fire variability in the model, and that wasn't there within the multi-state modeling. So we get this nice piece as well.
Chelsea, I just want to say that it's about time. Yeah.
Yeah, perfect.
Thank you.
Great. So I'll end with saying that we're working on that right now. There's 14 different models to consider for this, because we have decided to vary the baseline hazard functions that we use, the frailty distributions, and the frailty forms. So there's quite a lot. We've done this work using Bayesian analysis estimated via JAG. So I'm still in the process of kind of analyzing the output here. And essentially, there's a lot of beautiful extensions with this work, right? We can think about extending the number of phases, incorporating better spatial effects, and even thinking about adding time varying predictors as well, which makes sense with a lifetime. Yeah, thank you.
Yeah, thank you very much, Chelsea. So are there any questions?
Yeah, we have one question here in person, Judith.
Very interesting presentation. calculations on the amount of work that is done. The question is, again, I come back to saying it seems to me that this, in all the modeling efforts that are done, there is a divorce or separation, if you will, between these things change over space and time. And most models just take care of the time and assume that the space is taken care of by assuming some homogeneity on an ecosystem, which doesn't necessarily represent reality. So how in these models, the spatial variability of conditions, whatever the factors that may be, whether there is the frailty or using how the space is taking variability of the space is taken care of.
Yeah, so for what we were doing initially, we kind of used more crude spatial pieces, right? Where we're utilizing, not so much. I mean, we do have the kind of those distance variables, which help in some regard, but the fire to fire variability that we have with the fire specific frailties does pick some of that up. We do want to consider adding in those better spatial effects in order to catch that, because especially in that district, there is quite a difference between the fires that are happening in the south versus those that are happening in the north, because of the fact that we have the boreal shield and then up top we have the plains, right? So there is a need for it. And it's something that with that data, I had looked at using inline and everything before, but to incorporate it all together in one is not something that I've sorted it yet, but it's definitely on the radar.
Okay, thank you. Thanks very much for the sake of time. So let's leave remaining questions to time after the session. And thanks very much, Chelsea. And so now we proceed to the second talk, which kind of looks at the different types of resiliency and adverse events associated with COVID-19 and biosurveillance. And the speaker is Ocean Day from University of Texas, El Paso.
Okay. Can you hear me?
Yep, everything's good.
Okay, thank you. Thank you, Willia, for the introduction. Good afternoon, everyone. I want to thank the organizer for giving me this opportunity to present my ongoing work on the evaluation of COVID-19 vaccine acceptance in the US using complex network analysis. It's kind of, I don't know how, it doesn't fit very well, though, in this conference, but thank you so much. This is a joint work with Shopratik Kundu. He's from University of Texas, MD Anderson Cancer Center. Little bit background. So in the US, COVID-19 vaccines are available for everyone 6 months and older. And according to Center for Disease Control, around 226 million people have been fully vaccinated as of October 2022. And this proportion is around 68% of US total population. However, the vaccination coverage numbers varying according to age group, sex, geographical region, and different other socio-demographic factors. And a number of studies has also been conducted to evaluate the relationship or correlation between socio-demographic factors and COVID-19 vaccine acceptance decisions. However, most of the studies have been conducted are mainly focusing on the total population as a whole, but the factors which influence COVID-19 vaccine acceptance may vary in micro level, or think about the county level or FSA level in Canada, for example. So therefore, it is important to understand how this COVID-19 vaccination programs perform in the county level, and how does different socio-demographic factors influence the decision in the county level. So in this study, we actually focusing on county level analysis of COVID-19 vaccinations. Okay, so particularly we want to study or evaluate the following questions. First, how does or to what extent do socio-demographic features, for example, higher education, household income, geographic region, determine the decision to take the vaccines. And do the neighbors influence the decision? And if so, how or to what extent? And third, can we develop a community detection algorithm to group these counties in different clusters by accounting complex nonlinear vaccination relationship among different counties? And to do this, we actually apply the following analysis. So notice that we want to focus on county level information, and then finally we want to combine all this information together. So to do this, we actually construct a complex network where nodes represent US counties, and edges are constructed based on two parameters. One is the distance between two counties, and another one is vaccination rate of different counties. And we evaluate the statistical significance of different socio-demographic factors based on exponential random graph model. Okay, and finally, we actually propose a topological data analysis based clustering algorithm for this clustering, for this grouping of these counties. So let's focus on how we construct this vaccination network. Suppose we have set C, which contains all US counties, and we have a set I, which contains the percent of people who are fully vaccinated. And D is the pairwise distance, geographical distance among different counties. Okay, so we construct this vaccination network based on the following steps. So each counties in C actually makes the nodes in the network. And two nodes, say node I and J, are connected by an edge if the following two conditions are satisfied. So if both counties I and J have lambda or more COVID vaccination rate, and if the distance between these two counties are less than delta. Okay, so that is the adjacency matrix can be written as, that is, two nodes or two counties I and J are connected if they have lambda or more vaccination rate, and the distance between them are less than delta. Okay, so or zero otherwise. So for example, here we have two network. We constructed two network, one for age group 18 or above, and one for age group 65 or above. So as you see that the network 18 is very sparse, and here network 65 is really dense. And here we actually chose our distance parameter 50 miles. So the idea of choosing 50 is that, so around 50 miles, people might use same restaurant, or people use same stadium to enjoy sports, or they use same bars. Like they actually talk to each other in different factors, including COVID-19 vaccinations. That is, people might influence each other, right, around 50 miles. So later on, we will actually check different delta, and how these different delta influence the consistency of the result. So let's just focus on these two networks. So as you see, again, this network 18 is very sparse, and almost 50% of the nodes are disconnected. But for network 65, it is very dense. And you can also see these points are the nodes or counties of the network, and the color and size actually vary according to the vaccination rate. So in particular, a county with higher vaccination rate represented by a bigger and bright color points. Okay, so, and this is the summary statistics of these two networks. So both network has equal number of nodes, 3192. So as you see that network 18 is very sparse, therefore it has a very small number of edges compared to the network 65. And consequently, the mean degree is very small for network 18 compared to network 65. So the plot shows the degree distributions of these two networks. So as you see that the most of the nodes in network 18 has 0 connection or 0 degree. But for network 65, so there are significant number of nodes have moderate to large degree. So beside this degree distribution, two important characteristics of this vaccine acceptance network is average neighbor degree and assortativity. So the idea of average neighbor degree is we want to see the relationship between one node's degree and its surrounding node's degree. Okay, so we want to see how the degree of a particular node influenced by its surrounding node degree. Okay, and in addition, it is important to understand how a node with a particular characteristics is connected with a similar node. For example, we want to see whether a node with higher education rate may be connected or not with another node with higher education. Okay, so in social science, this is also called homophily in social network, and the coefficient actually measure the extent to which these properties connected to each other. So I'll show you the result in a second. So let's look at the neighbor's degree first. So left panel shows the result for network 18, and right panel shows the net results for network 65. So as you see, the top left figure, that the nodes with higher degree tends to be connected with another higher degree node, and nodes with lower degree tends to be connected with lower or medium degree node. And this is also obvious for the network 65. And we also compute average neighbor degree for different census region in the US. So for example, in this figure, you see that almost like all this region has very small average neighbor degree, except the Northeast. But for network 65, the average neighbor's degree is around 10, except the region West. So we can say that for elderly people, like network for 65, so the neighbors may influence the decision of taking the vaccines. So the neighbors might have like significant influence of taking the vaccines for the elderly people. And now let's focus on assortativity. So as you see that for degree, the properties degree, the coefficients are very high, right? That means, again, a node with higher degree tends to be connected with another higher degree node. Similarly, a node with lower degree tends to be connected with another lower degree node. And for the state, it implies that so two nodes in the same state tends to be connected each other. Okay, there is a high probability of two nodes in the same state to be connected. And finally, for two nodes with similar COVID-19 cases or similar education level or medium household income have moderate likelihood to being connected by an edge. So that means that the nodes with similar characteristics tends to be connected by an edge, in summary. So now we want to focus on the statistical significance of different socio-demographic features in formation of edges. So for this purpose, we actually apply exponential random graph model. So here we have two types of covariates. One is structural covariates, for example, existing edges or existing triangles. So the idea here is, so whether or not the existing edges or existing triangles or higher order network structure influence to form a new edge. And for covariates here, numerical covariates, we have, like, for example, median household income and so on. So we can reorganize this model in terms of logistic regression framework. So as you see that the logit of probability of being connected can be written as this function. So the log of probability of being connected divided by 1 minus not being connected. That is kind of a logistic regression framework. And the expected of Yij equals to probability of being connected. And we can quantify this probability using this equation. So we estimate this ERGM model based on MCMC-based likelihood estimation techniques using the R package ERGM. And we interpret the coefficients similarly as logistic regression by odds ratio. So,
Question 3 minutes, okay.
Yeah, sure. So here the results like output of the parameters. So as you see that most of the parameters are significant. And here, as you see we only use edge covariates, as a covariate because of computational complexity. And we can interpret these edge coefficients similarly to the intercept of a linear regression. So that is when there is no covariates in the model, the probability of occurring an edge, for example, for network 18 is this 9.5, 10 to the -5, very small. As you see that it is very sparse network. And for network 65, it is 0.001. So it is very high. Okay, so for higher education, we can quantify the parameters by this odds ratio. So that means the odds of forming an edge increase by around 3% if we increase 1 unit in the percentage of adult higher education. Okay, and as you see that this higher education is not significant for network 65. And then for network 18, so if we increase the income around 5,000, so the odds of forming an edge increase by 11%. And for network 65, it is around 5%. Similarly, COVID-19 cases also have significant positive influence on edge formation. And we also use another variable for what is US Census region. So as you see that here, it's kind of a dummy variable approach. So here, Northeast region, we consider it as a base level, and we compare Northeast with some other 3 regions. So as you see that for network 18, so 2 nodes in Northeast region are more likely to connect compared to the other 3 regions. But for network 65, South, 2 nodes in South are more likely to connect compared to the Northeast. And there is no significant difference between Midwest and Northeast. So this is mainly because maybe the elderly people lives combined like in a group in the South region in the United States. So I'll skip this TDI approach. Maybe let's quickly go through the results. So we apply this TDI-based clustering algorithm of our networks, of these 2 networks. As you see that in network 18 is dominated by 3 clusters. So the green cluster actually has very low COVID vaccination rate. So as you see here, this is the cluster number 1. It is a very low vaccination rate. And for network 65, it is dominated by 2 big clusters. So this green cluster has very high vaccination rate. So let's keep this. And in summary, what actually we found that the socio-demographic factors actually significantly influence COVID-19 vaccine acceptance decisions. And we propose a topological data analysis approach to cluster different counties in different communities. So although we actually focusing on COVID-19 vaccine acceptance network, this approach can be applied to any single layer network. For example, the like environmental network also. So thank you so much for your attention. Let me stop here.
Thank you, Ocean. So we ran out of time, but maybe we can have just one short question. So it will leave.
Does anyone local want a question, or anyone on Zoom?
I have a question.
Yeah.
Okay, so about what are the explanatory variables that you put in your ERGM model? Did you put the features of the network as explanatory variables?
Oh, yes, we only use the edge. So because I tried to include the triangles of the network, but it takes too much time. So that's why for this, like for current, I only use the edge, number of edges in the network. So
Thank you.
yeah, so here only edges. Yeah. Thank you.
Okay, thank you. Thank you, Oshim. I just want to say that the same idea could be used when you add climate variables with and then do COVID-19 severity. Yeah,
Yes,
so
thank you.
just the same idea when you can create a graph out of it.
Yeah.
Okay, okay, thanks very much. And the next speaker is Dorcas Afori-Boateng, and she will talk about power grid resilience with respect to different type of adverse climate events. Thank you. Dorcas?
Can you hear me now, everybody?
Yes.
Okay, awesome. So thank you very much, Yulia. Thank you very much, everybody, for making time, for giving me the opportunity to also present a long ongoing research to understand how power grid networks respond, particularly in the face of weather-related or climate-based attacks. From recent news feeds, I know we are aware currently, if you are not, on several areas in the US and in Canada in particular, undergoing certain heat wave, climate changes. And it's quite interesting to think about how power grid networks would respond in the face of these scenarios and contingencies. Particularly back in 2021, we all remember how Texas went somewhat partially dark in the face of excessive snowstorms, which was not expected by the energy and grid authorities. So I'm going to present a bit on motivation, which I've already stepped into, and give a brief introduction on methodology that was proposed to understand how the grids would fare in the face of the academic climate attacks, and show some preliminary data analysis that we have as far back as from another kind of weather-related attack, and explain how that was applied to our data analysis, and discussion on ongoing and future research that we have in our toolbox. So technically, power grids are not graphs or networks. They are physical components that are made up of transformers, generators, which are connected one to another by transmission lines. But in the view of how they are constructed, they can be viewed as graphs, they can be viewed as networks, and has already been presented. I don't have to talk more about what network analysis has to do in this phase. But depending on what the design of the grid is, depending on how the grid is structured or built under hazardous attacks, which design will be more robust and be preserved and continue to be more productive is a question that we seek to address, and to understand how robustness could fare to inform on grid efficiency and productivity. So like I said, heat wave is one particular climate or weather-related attack that we considered. And as far back as in 2016, in Texas, which is our preliminary study ground, Hurricane Harvey severely devastated partly the coastal line towns, and it's spread up across. But we also took into account this data and how it's fared on the grid in general. So the impact of natural hazards would require some complex, non-stationary, non-separable spatio-temporal covariance structure studies, which is not primarily present if we are going based on traditional Euclidean matrix, because they would not be able to capture pertinent information related to the non-stationary complexity of these events as as they are. So we introduce a data shape-driven analysis of these power grid systems and affect each one of these under different adverse atmospheric events and try to capture what what shape-related information is present, what shape-related information would be noticed under the severe attacks that we simulate or generate in the course of our analysis, and how this can best inform policyholders for future policy formulation. The method that we considered here is based on topological data analysis, which allows to study the systematic, qualitative, and quantitative geometric structure of data as is viewed lens-wise. One of its main tools, that is what we primarily focus on, is the persistence homology that allows to study data in the face of nested simplicial complexes, which can be thought of as placing numerous multi-lens sieves on the data and trying to capture useful topological information as is faced at different threshold or sequential levels. So in the phase here, the particular type of filtration scheme we place is the vitreous ray filtration, which allows us to set a threshold at different time stamps and capture information on what topological image is viewed or is present on the scale of the data, which we have translated into the graph. And at different thresholds, we capture different topological images, topological information, but we will not just be interested in capturing the information, we are interested in how they are also summarized. There are three main topological summaries that we considered for analysis. We only focused on the first and the third, which are the Beatty numbers and the persistence diagram, and further I'll talk about what each one of these mean. Now, the Beatty numbers allow a count of connected components and p-dimensional holes as is present in the filtration process. At each level, you can count how many types of a particular Beatty number are present. And I'm saying types because there are different types of Beatty numbers. If your Beatty number of interest is the number of connected components, then you are looking at Beatty 0 values. If you are interested in the number of one-dimensional holes, you're going on to Beatty 1. If you're interested in two-dimensional holes, you are graduating in that same order all the way to the p-dimensional holes that you are interested in. And this is a clear illustration of how they appear in different screens for the filtration process and how you can count how many of each type of Beatty number is present. Apart from the Beatty numbers, another very interesting summary for topological features as is present during the filtration process are the persistence diagrams, which capture the birth and the death of different topological images. I'm saying birth and death because at each threshold set for the filtration, we can identify or we'll be able to see the emergence of a particular shape. And as the threshold scheme increases, it either still remains or it's phased out into another shape or into another object, whereby we say it has died. Now, we are interested more in shapes that have a long liveness, ones that live long in the scheme of the filtration, because the longer it lives, the more persistent or the more important that image or that shape or that topological feature captured is. But if it's one that is born in one threshold and dies in the very next threshold, then that falls under the clause of topological noise, one that doesn't hold valuable information, and so we can completely ignore it. Now, depending on two data streams you can generate for these two different data streams, two different persistence diagrams, and you can compare or find the similitude between these two. We can do that employing the Arth-Wasserstein distance, which allows to compare how similar or dissimilar two different images are. In this case, the persistence diagrams D1 and D2. And so if we have a power grid network information, let's say in 2002, comparing that again to the same information in 2003, we can compare how it has progressed over time, whether it has deformed, or whether it is still active and doing very well. And we do that in the face with their persistence diagrams. With the Beatty numbers that I just mentioned, we can also build robustness metrics to measure how the grid is able to sustain its production responsibility, even in the face of attack. And we capture that with the normalized value of the change in the Beatty numbers. So depending on what Beatty numbers you're interested in, Beatty 0, Beatty 1, which was our focus here, we can calculate how they change over time. And we do the same with the Wasserstein distance, which, like I have said initially, is comparing the persistence diagrams again over time as we are scaling through the scheme of our attacks. So like I've said, a system can be more resilient if it is preserving a lot of its original properties, even in the face of attacks. And properties here face physically to how productive it will be, even in the face of attacks, that it can withstand, whether it is heat wave and there's too much overheating in the grid, and so it has to shut down because it reached a threshold, and per system design, it is not able to supply to the demand that the grid has. Otherwise, if it is able to still maintain its responsibilities, it's considered more resilient, and that is what we are trying to measure with the tool of TDA. So our approach would examine how the Beatty numbers for the preliminary study is preserved over time, whether it is doing a good job or there is some form of threshold where the grid totally collapses. And we'll do the same, repeat the same analysis with persistence diagram and see how that would also change over time. And like I said, our change is going to be measured in terms of how the Wasserstein distance moves across board. So for our preliminary data analysis, we considered a 2000 bus Texas synthetic power grid network. Synthetic because real data power grid network is very hard to come by. There are a lot of confidentiality barriers that have held back, but fortunately, there are some synthetic grids that are built even on the footprint of the actual, not exactly, but they try to be close. So for this particular data set, 2000 bus means that there are 2000 nodes. The number of connections amongst them, I don't have that here, but it's quite a lot. I'll show the diagram with that. A total of 1,500 substations that correspond to 2,000 nodes in the 2,000 buses. And we have edge weights aligned with the grid view, the graph view of this grid network. And we place on them the mean, the MVA ratings of the transmission lines as the edge weights that allow us to move through the phase of filtration and still generate the different views for capturing the topological summaries. So like I said, for this particular data, we merged what happened in 2016 to Texas, particularly in the face of Hurricane Harvey, compared data generated from the National Weather Service and NOAA in particular, and how impact was measured, which different locations within Texas were impacted, and which grid networks were in that same, in those locations, in order to simulate how a synthetic grid would be impacted on the same view of what actually happened. So we can mirror out the impacts, how it was affected, and whether our metrics are able to still capture the fair enough view in order to inform policyholders for future use. So
this time, yeah, just please wrap up. Okay.
We simulate the same view for the synthetic grid network, and as the blue dots, which are the actual, are turning to red, that's a view of the fact that these are within the range of areas that get impacted by the hurricane and the rainfall that come after it. We capture how each one of these is phased out differently, depending on the number of nodes that are going out or having the red button. We measure their change in Beatty values and also the change in the Wasserstein distance. And the first thing that we notice is whether we are going with the Wasserstein or the Beatty 1 change value metric. We tend to produce the same output. The only slight difference is that on the face of counting for the change in the Beatty 0, there's some slight difference there. But as we increase the number of nodes that are being impacted overall to as much as 1,045 nodes being kicked out or being attacked in the face of this event, realize that the grid totally loses its ability to sustain production and be even classified as robust. That's in the area where the higher values really measure severe impact on robustness. So generally, as we have demonstrated, the phenomenon of capturing weather-related attacks as they impact power grids is complex, but topological data analysis affords a leeway out that enables us to quickly capture how the system topology would be impacted overall, even at the local level, at the minutest level, because topological data analysis allows not just to study global impact, but impact as it will appear individually within the entire stream of data we have, and that is more suitable for the case of power grid networks. And for our future and ongoing research, let me put that well, we are trying to narrow the same understanding to the Pacific Northwest, particularly on the 10,000 bus synthetic grid of California, Idaho, Oregon, Washington, these four, to generate how resilient they would be, trying to understand that in the face of particularly where climate or weather-related attacks, how these grids would be able to still maintain their production requirements, at which point is it a total collapsing and no return points, and what can be done to create mitigation outlays out. And so that's technically where we are going right now. This is not just going to phase out in rain, but we are considering other hazardous events that include heat wave as it's ongoing, and to integrate other energy sources like solar, wind, and other distributed energy resources, and capture the information and how they impact not just the power grid's ability to produce, but how the economy would also be impacted in general if this goes unchecked. And this is where I will stop for questions if anybody has any. Thank you very much.
Thank you very much, Dorcas. So